声了，就是声音就会收进去，然后这样子再。然后中间那边
this is really a dream come true because we have been waiting for Professor Lo to find time to visit Hong Kong. Since the days when we started brainstorming about starting a undergraduate program in financial technology. In fact, this program is undertaken by the Faculty of Engineering, Department of Systems Engineering and Engineering Management, with collaboration from CUHK Business School, Department of Finance, and also the Faculty of Law. Now, while we were brainstorming about our program, we actually sent Professor Lo various emails and questions, and we have been extremely appreciative because we always get prompt responses from him, and they have been tremendously helpful. So we're really happy that with today's opportunity, it actually brings CUHK Business School and the Stanley Ho Big Data Decision Analytics Research Center, which is in the business school, but also with strong participation from engineering school. We bring these two schools together to host today's event. This is going to be the first lecture of today. This is the academic lecture. There will be a public lecture this afternoon. And we are really looking forward to both talks by Professor Lo. And actually, both talks are being webcasted as well. So I understand that a finance seminar, it's a more interactive setting, unlike engineering school seminars where we try to defer the questions to the end. So I guess today we'll adopt, since we're in the business school building, we'll adopt your modality and we'll run this seminar in a more interactive manner with agreement from Professor Lo. Okay, so now I wish to hand over to Joseph, Professor Joseph Cheng, to introduce our speaker today.
Okay, thank you, Helen. Let me welcome you all again to the academic seminar organized by the Finance Department of the CUHK Business School and also the System Engineering and Engineering Management Department. It is our honor to have invited our guests as speakers for today's seminar. As the Charles C. and Susan T. Harris Professor at the MIT Sloan School of Management and Director of MIT Laboratories of Financial Engineering, he received his PhD in economics from Harvard University. Now, before joining MIT's finance faculty, he has taught at the Wharton School of the University of Pennsylvania as W.P. Carey Assistant Professor, as well as W.P. Carey Associate Professor of Finance. Now, our eminent guest has published numerous articles in top-tier journals spanning across various academic disciplines, such as finance, economics, medicine, as well as engineering, just to name a few. He has also published or authored several books, including Adaptive Markets, The Evolution of Financial Market at the Speed of Thoughts, The Econometrics of Financial Markets, A Non-Random Walk Down Wall Street, Hedge Fund, and an Analytic Perspective, and also the Evolution of Technical Analysis. He is currently co-editor of the Annual Review of Financial Economics, associate editor of the Journal of Portfolio Management, Financial Analyst Journal, and the Journal of Computational Finance. Of his many awards, which include the Sloan Foundation Fellowship, the Paul A. Samuelson Award, the American Association of Individual Investor Award, the Granham and Dodd Award, the 2001 IAFE SunGuard Financial Engineer of the Year Award, and also the 2010 Harris M. Markowitz Award, and awards for teaching excellence from both MIT and Wharton. Now, dear colleagues, without further ado and with great pleasure, please welcome Professor Andrew Lo. Okay.
I want to start by thanking Professor Cheng for that wonderful introduction, and I'm very impressed that you used no notes, so I could barely remember my own name at this point, so thank you for taking the time. And I want to thank Professor Meng and Dean Chan for inviting me here today. It's really an honor and a great pleasure for me to be here giving this lecture. This is the first time I've come back to Hong Kong since I was born here 58 years ago. And I'm just really thrilled to be here for this event. I should say that the reason that I haven't come back is really mainly because I'm a very bad traveler. I don't like sleeping in hotels. I can't sleep on airplanes. So I may actually be a little bit groggy today. I apologize in advance because I'm quite jet lagged. But I'm here and I'm really thrilled to be with all of you today for reasons that you'll understand once I start talking about some of the work that I've been doing. Because I've actually, over the last few years, been doing more and more across different fields, particularly in engineering and in finance. And I think that having both the business school and the School of Engineering represented is a great honor and a great pleasure because you'll see a lot of connections in terms of the things that I'm interested in, and I suspect things that all of you can accomplish. So I'm going to start by talking a bit about this work that I've been doing over the last few years on adaptive markets. And it's related to this book that I recently published, Adaptive Markets, Evolution at the Speed of Thought. And I want to apologize in advance for the length of the book. It's about 500 pages long. And the reason for that is that when I first started writing it, my publisher looked at some of the early drafts and was very discouraging. And he said, I want to just mention something to you. Every equation that you include in your book will divide the number of readers by half. And so I made a really big effort to include no equations. There's not a single equation in the book. But as a result, it's 500 pages long. It takes a lot more time to describe. And it really has to do with this idea that I've been struggling with ever since I was a graduate student. And the idea happens to do with this big divide between this idea of efficient markets, that financial markets fully reflect all available information on the one hand, and at the opposite end of the spectrum, the fact that people behave irrationally, that we are all driven by fear and greed. And I'm sure that all of you are aware of this debate because it's something that even as a graduate student you're exposed to with various different camps fighting with each other. And it reminds me of the days when you're a child and you're listening to your parents argue, and it's very frustrating and disturbing because you love them both and you just wish they would stop fighting and get along. And so what I've been trying to do is to reconcile these two different approaches to understanding financial markets. And what I want to share with you today are just a few aspects of how, at least in my own mind, I've been able to bridge that gap. It started out as a kind of a journey when I was a grad student because then I learned, like most of you, that markets are efficient and people are rational. And over the time that I was a student to when I became an assistant professor, all sorts of evidence to the contrary came about. And I tried to understand which particular path to follow. And so, like many of you, I started out on this personal journey with efficient markets and rational expectations, and then started learning about behavioral finance and psychology, which then brought me to the cognitive neurosciences, and then to artificial intelligence and bounded rationality. And I then started digging a bit deeper to try to understand the evolutionary and biological origins. And ultimately, all of that finally brought me to a reconciliation, which I call the adaptive markets hypothesis. And so what I'm going to do today is to bring you along that journey and describe a few of the milestones along the way to try to explain to you how I've come to reconcile these two different schools of thought. And now, I really didn't start out trying to go through all of these different disciplines, but it was because I kept searching for the answer and ultimately was dragged from one discipline to another to be able to understand how it is that people make decisions in financial markets. So the idea behind the adaptive markets hypothesis is to get those two parents to stop fighting and get along, and to do that in a way that is intellectually satisfying. So let me give you a quick summary of how I'm going to do that. The basic idea behind adaptive markets is that the traditional economic framework that we use is flawed. It's not wrong, but it's incomplete in the sense that it ignores a pretty significant body of research and behavior about how humans make decisions. And the basic principle that I followed in thinking about this is not to use a physical analogy, which many of us economists like, the physics envy that I'll talk about in a little while, but rather to look at the economic systems that we study as biological systems And in those kind of systems, in a stable environment, stable economic relationships will emerge. And that's what we think of when we think about efficient markets. But when the environment is dynamic, then those relationships no longer hold. And I'm going to argue that the current environment is highly dynamic and that we have to start adapting to those changing environments. And that process of adaptation is what we observe and what we start thinking about. You know, politicians often say it's the economy, stupid, that drives political decisions. But actually, I think that biologists should be telling us economists that it's the environment that's driving decisions. So the purpose of this framework that I'm proposing, the adaptive markets hypothesis, is to give us a way of thinking about the environment and how we adapt to it and then ultimately drive the kinds of financial market dynamics that we observe. So that's a quick summary. And as I said, I'm going to give you a few instances of each of these different ideas across the various different fields. So there's going to be a three-part presentation, and I'm not going to go through each of the different parts. I have a fairly long set of notes that I'll be happy to provide to you. But the three-part presentation is really meant to try to convince you about this new framework. And because I come from a rather quantitative field in finance, I've got to start with the mathematical framework. So that basically just demonstrates that I've actually spent the time thinking through the quantitative implications. But in my view, that's not the most important part of this framework. It's really thinking about the broader aspect of how human behavior works. And then that second part is going to be a neuroscientific perspective. Over the course of the last 10 to 20 years, there's been a lot of progress in the neurosciences. And I want to use some of that progress to understand how economic phenomena can be modeled. And finally, the last few minutes of my talk, once you understand the first two basic areas, it'll be very easy to see how they apply to specific financial contexts. So I'm going to talk about the risk-reward trade-off. I'll talk about the traditional economic paradigm and think about ways of extending that using these ideas in adaptive markets. So let me start with a little bit of mathematics. And I'm going to first tell you that I'm not a theorist by any means, but I started developing some of these ideas because it turns out that some of the analysis that we use in econometrics is actually very applicable to modeling human behavior. So I'll start with the basic observation that in grad school, even today, we teach our students to think about economic behavior from the point of view of the work that was developed in 1947 by Paul Samuelson and von Neumann and Morgenstern, and that is expected utility theory. Maximizing expected utility subject to a budget constraint. Uh-oh, I just realized that when we transferred over the file, I didn't check to see whether the fonts transferred over. So this is going to be actually a very short mathematical presentation because we're going to skip over a lot of it, given that the notation's not going to be there. So this theory of economic behavior has become so prevalent that now economists are modeling all sorts of things. So it's really now the economic theory of all behavior. For example, economists have used this idea of maximization of expected utility. They've used it to model things like marriage, suicide, drug addiction, divorce. All aspects of life now have been modeled by economists. And in a way, it's very impressive, but it's also a bit of a sign of arrogance because a lot of these ideas really, in my view, don't apply to those contexts. But we like to think about them anyway. You know, this idea of drug addiction as being rational is a bit hard to fathom. And there are some interesting predictions that seem to accord with some of the data, but the underlying motivation is so different that it's really hard to make sense of it. So I'm going to try to do that in the context that we're going to just derive in a few minutes. But all of that is to say that we now have a theory of human behavior that we economists like to call Homo economicus, economic man. And it's really troubling in one sense because it seems to supplant a lot of what other disciplines think of as behavior. And you'll see some contradictions in a few minutes. So the contradictions have to do with what happens when you actually look at the data. And much of my work early on was focusing just on financial data. And in some collaborations that I engaged in with Craig McKinley at the Wharton School, early on, we looked at some of the modern theories of financial markets like the random walk hypothesis and found that they actually predicted very poorly how the data behaved. And so many other psychologists and neuroscientists and behavioral economists have come up with other violations of the axioms of expected utility theory. And it's hard to understand unless you start looking at these behaviors in a more specific context. So I want to give you one example focusing particularly on this notion called probability matching. This is a very old kind of behavior that unless you actually study behavioral economics, you probably wouldn't come across. But let me tell you what it is. It's a particular phenomenon that is it was first documented in an experimental laboratory in a university setting. And it involves a very simple game. The game is this. I have a coin in my pocket, and I'm going to toss the coin, heads or tails. You're going to have to guess what the outcome is. And if you guess correctly, I'll pay you $1. And if you guess incorrectly, you pay me $1. And we're going to do this a repeated number of times. Now, the coin that I use is my own, and I will tell you right now that this is not necessarily a fair coin. It could be biased. But you don't know what the bias is. So we're going to just go ahead and play the game. And the question is, what is your ultimate strategy? Now, suppose that the coin is biased 75-25. You don't know this, but it is. And after we play 20 or 30 times, you notice that the coin that I'm using is coming up heads 3 times more frequently than tails. You observe this. So once you observe this, what should your optimal strategy be? What should Homo economicus do in that case? Anybody? Guess heads all the time, right? Because guess is more likely to come up than tails. And so if you want to maximize your expected winnings, you should guess heads all the time. That's what you should do. It turns out that in the laboratory, people don't do this. What people do is this. They randomize. But here's the interesting thing. They randomize with the same probability, 75-25. They guess heads 75% of the time, and then they guess tails 25% of the time, which is definitely not as profitable as guessing heads all the time. And what's even weirder is that if in the middle of this game you secretly switch coins, and now instead of a 75-25 coin, you use a 60-40 coin, well, in that case, after another 20 or 30 trials, people will start guessing heads 60% of the time and tails 40% of the time. That's weird. And finally, what's even more strange is that this behavior, which is called probability matching, this behavior has been documented not just in humans, but in ants, fish, pigeon, mice, monkeys. Virtually every species on the planet that is capable of choosing A versus B, when you present them with an appropriately structured task, they will engage in this very irrational behavior of probability matching. Now, you might ask, how do scientists figure that out? How can you tell that fish engage in probability matching? Well, it turns out that there's a psychologist years ago who studied goldfish. And the way that the psychologist did it was they put goldfish in a tank, and they decided to feed the goldfish either from the left side of the tank or the right side of the tank. And they would randomize by feeding the fish 75% of the time in the left side, 25% of the time in the right side. Now, if you were a rational goldfish, what you would do is to always stay on the left side of the tank. But in fact, the goldfish probability matched. And when they changed the probability of 75-25 to 60-40, the goldfish changed as well. So when I read this, my co-authors and I started wondering, is this behavior really irrational? Or is there some underlying logic for it? And it turns out that actually we think there's a logic. There's a biological motivation for this kind of behavior. So that's where the mathematical model comes in. And let me be brief about this because I do think it's going to be hard to follow without the notation. I want you to consider a very, very simple model of biological evolution that is actually not found in nature in its precise form, but it's a mathematical simplification that gets at the heart of what evolution really is. I want you to think about creatures, not necessarily humans, creatures that live for one period and then they die. And when they live for one period, they have one decision to make in their lives, and that decision is to make a choice between A versus B. I won't even tell you what that choice involves. Maybe it has to do with nesting behavior. Maybe it's foraging behavior. Maybe it's how they decide to find shelter when they're confronted with a particular threat. All you need to know is that when they choose A, they will get a certain number of offspring, x of A, which is a random variable. And when they choose B, they'll get a certain number of offspring, x of B, and x of B is a different random variable. So this directly links behavior to biological outcomes, reproductive success. Now, what I've just done is to sweep under the rug what biologists really care about, which is how does behavior lead to reproductive success? As an economist, I have no interest in the biology. All I want to know is if you choose this, how many offspring do you have? If you choose that, how many offspring do you have? So that's what I've done. I've just simplified all of the biology. And I've also made the following assumption that is a kind of a perfect genetic type of transmission mechanism. I'm going to assume that the parents have a certain behavior that is perfectly copied by the children. Now, in a minute, I'll describe what I mean by behavior, but this is something that does not exist in biology, at least in most cases. Some bacteria may satisfy this, but for now, I'm going to assume this very hypothetical setting where the children behave just like the parents. So let me explain what I mean by behavior now. So there are these two choices, A versus B, right? By behavior, I'm going to mean how do you choose A versus B? How do you make that choice? And I'm going to assume that you make it with a very simple Bernoulli trial. You toss your own coin, which may be biased, but that's your coin, and you flip it, and if it's heads, you pick A, and if it's tails, you pick B. And just to be clear, the probability for your coin is given by the parameter f. So f is your probability of choosing A. And that's what I mean by behavior. It's that parameter f, okay? And now you can understand what I mean by this perfect genetic transmission. Once an F, always an F. So if you're an F, your children are going to be Fs, and their children are going to be Fs, and so on and so forth. So just to be very clear, suppose that F is a given value. Then when you take a draw and you let your dice roll, you're going to get A with probability F and B with probability 1 minus F. And x of A and x of B are these random variables that, in this case, x of A produced 3 offspring and x of B produced 9 offspring. All right? Very, very simple kind of behavior. Now, I'm going to include in these possible values of f every number between 0 and 1, including 0 or 1. So for example, if you're the type of person that always chooses A, then for you, f is equal to 1. And then your children will always choose A, and they're going to be f equal to 1, and your children's children will be f equal to 1, so on. Okay? Now, I'm going to just assume some joint distribution for xa and xb, but otherwise, I won't really spend much time focusing on it for now. So this very, very simple model of biological transmission is going to be repeated over many, many generations. So I'll start off with a particular generation. I'll let them reproduce, and their children will reproduce, their children's children will reproduce, and after a few generations, I get a whole bunch of Fs, right? So now, here's the experiment. The experiment that I'm going to do is to start off with all possible values for F in a given population. So I'm going to have people that always pick B. For them, F equals 0. I'm going to have, in my population, people that always pick A. For them, F equals to 1. And I'm going to have all possible Fs in between. And I'm going to have the same number of them to start off with in generation 0. And then I'm going to let them reproduce. After many, many generations, as they reproduce, I'm going to see what the population looks like. And after a number of those generations, I'm hoping to see a pattern. I'm hoping to see whether or not there's a particular kind of F that survives this process of evolution. So in this case, you can see that the green dots, F equal to F sub 4, dominates. And when I do that, I will then be able to conclude that, this behavior, F sub 4, is the behavior that survives from an evolutionary perspective. That's the exercise that I'm trying to conduct. I'm going to start them out having all the same representation of Fs, and after many, many generations, I'll let them reproduce and see what happens, and ultimately I'm hoping to see a particular F emerge. as the single behavior that dominates the population. Now, before I show you the results, I need to make one more assumption, which is the joint distribution of XA and XB, right? And so here's what I'm going to assume. I'm going to assume that the joint distribution of XA and XB is identical within a given generation and independent and identical across generations. So let me explain that, all right? When I say that it's identical at a given generation, what that means is that if you and I are in the same generation and we both choose action A, we will both get the same random variable XA, the same one. And if that random variable is 4 offspring in this generation, that means when you choose A, you get 4 offspring and I get 4 offspring. Now, instead, I could have assumed that they're independent and identically distributed in a given generation. In other words, if you pick A and I pick A, we both get the same distribution but independent draws. So you might get 3 and I might get 7, but the distribution is the same. It has the same mean of 5 and variance of 2. That's not what I'm assuming. I'm assuming that they're identical in a given generation. And the biological implication is that you and I are in the exact same ecological niche, so that when you do the same thing that I do, when we both choose A, we actually face the exact same outcome. That's important for reasons that I'll explain in about 10 minutes. But across time, I'm going to assume that one generation is statistically independent from another generation. So every generation has its own draws of XA versus XB. Okay. So these individuals that I'm modeling are otherwise mindless. They're choosing A versus B randomly. There's no optimization. There's no forward planning. There's no economic considerations. They're just completely random. And what I'm going to try to do is to ask the question, which of the different values of F survives after many, many generations? And that's the exercise, the process of elimination, which is what Ernst Mayr called evolution. Okay, so F star is what I'm going to be looking for, the particular value of F that maximizes the growth rate of its population, all right? And here's where the math can get a little ugly, actually literally ugly if I am not mistaken. Oh, actually, this came out. Let me see. Yeah, that's what I was afraid of. So yeah, these fonts did not come through. So let me just go to the example. The math is there, although it's not in these slides, but I'd be happy to send you the version that does have it. But let me show you an example of where the math takes us. I'm going to give you an example that has to do with a very simple ecology of rain versus shine. In this particular ecological setting, the two states of nature are it's 75% of the time sunny and 25% of the time rainy. And you who lived in this environment, you have to choose where to build your nest. And you have two choices. You can build your nest in the valley, or you can build your nest on top of a plateau. And let me describe to you what the implications are of choosing A versus B. A is the valley, and B is the plateau. If you choose to build your nest in the valley, where there's a beautiful stream and there's shade, and it turns out to be sunny, then the number of offspring that will survive in your case will be 3. Why? Because if you build your nest in the valley, there's water for your offspring so that they can drink, and the rays of the sun will be blocked by the shade in the valley so they won't be burned to death, and so they'll survive and thrive. On the other hand, if it rains and you build your nest in the valley, that's bad news, because the rain will cause a flood that will drown your offspring. And there's no escape from that flooding river in the valley. So that's the outcomes that you would experience if you decided to choose A. Now let me suppose you chose B instead. If you chose B, it's exactly the opposite. If you chose B and it's sunny, well, that's bad news because you're on the plateau, there's no water, and there's no shade. If it's sunny, the rays of the sun will burn your offspring to death. No survivors. But if you're on the plateau and it's rainy, that's wonderful because, first of all, the rain will provide water for your offspring, and the clouds will provide shade so that they won't be burned to death, and so your offspring will survive. Okay, so do you understand the setup? It's exactly the opposite in terms of your survival outcomes if you build your nest in the valley versus on the plateau. Now, let me remind you again that it's sunny 75% of the time, and it's rainy 25% of the time. So as a rational economist, where would you build your nest? What would be the answer? A, the valley. All the time? Yeah, of course, all the time. Because that maximizes the probability that your offspring will survive, right? That's a very easy calculation to do. Well, let me show you what happens in that case. And I'm going to do that by simulating a population. In particular, I'll simulate a population where you have a number of different species, a number of different behaviors, f equal to 0.2, 0.5, 0.75, 0.9, f equal to 1. The economists are here at the right-hand side, right? They're the ones that always build their nest in the valley. So let's see what happens. The economists, they're growing like weeds. They're growing incredibly. They're winning, and whoops. What happened? What happened? All the economists were wiped out the first time it rained. That's what happened. That means that that behavior can't survive. It is gone. The kind of selfish, optimizing, rational behavior in this circumstance cannot survive because natural selection won't allow it to. Now, what survives and thrives is a very interesting case. The F that maximizes population growth is the probability of it being sunny, f equal to 0.75. In other words, probability matching, that f is the value that optimizes the expected number of offspring regardless of whether it rains or shines. You see, what you're doing, these f.75 people, they're diversifying. Yeah, Utpal. We're not. We're not doing the optimization, but nature is. Mother Nature is. Because she's killing off everything that doesn't, like the economists. Her view is that economists really shouldn't survive. We won't talk about the wisdom of that. It's that they can't survive. That behavior is not growth optimal. The individuals are not doing the optimization. It's whether the behavior is suited to the environment. That's the key. It's a selection argument. It's only a selection argument, purely a natural selection argument, right? But now, let's think about this a little bit, and let's try to deconstruct the logic of what's going on. So I want you to imagine that this room is a population of f equal to 0.75 people, okay? And we're deciding where to nest. And so let's suppose that somebody appoints me, the vice chancellor, and I'm going to say to all of you, all right, here's what we're going to do. 75% of the time, it's going to be sunny, which means that the best bet is for us to build our nest in the valley. So here's what we're going to do. 3/4 of this room, maybe, I don't know, from this point over this side, let's all of us build our nest in the valley. And the rest of you over there, you go off and build your nest on the plateau. Now, I don't know how you feel about that, but it turns out that magically they go. And what it seems like they're doing is being very selfless. What you're doing is going for the good of the population, because there is a good chance that you will not survive. But in case it rains, you're the ones that are going to carry on the f equal to 0.75 tradition. Now, what I just described is a total justification after the fact. What's going on is we're all behaving randomly. But when you look from an outsider's perspective, you look at the population, it looks like altruism has emerged from this primordial soup of random behavior. So I'm going to do, so it turns out that the mathematics actually works out quite nicely. If you could have seen the math in the previous slides, you would have seen that when we plug in the statistical distribution of phi of xa and xb, and you do the growth optimization to calculate what nature selects, nature actually will select f star equal to p. In other words, the population that grows the fastest is the one that engages in probability matching. It turns out that if I change these parameters, if I change this example, the f star changes and the behavior changes. Our behavior, probability matching behavior, is the outcome of a very specific environmental context. Change the environment, and you change the behavior. So I'm going to do one more example before moving on to the neuroscience part. The example is going to basically change this behavior, and we're going to see now where the economists come from. So here's the change. Now, I'm going to assert that the joint distribution phi of xa and xb, where I said it was identical in a given generation, that assumption essentially caused all of us to exhibit a certain kind of riskiness, right? All the economists, they all decided to act in the exact same way, and they all built their nest in the valley. And as a result, when nature called for rain, it wiped out that behavior. So that kind of coordinated behavior can't persist. Well, I'm going to change the assumption about how nature behaves. So I'm going to assume that instead of the distribution being identical across individuals in a given generation, I'm going to assume that it's independent and identical across a given generation. What that means is that if you choose A and I choose A, we're going to get two independent draws from the same distribution, but they're independent draws. They're different realizations. That's all. That's the only assumption I'm going to change. If I make that one change, let me just redo the simulation for you. And again, I'm going to not be able to show any of this because it's not coming up, but I'm going to go back to this. Now, I'm going to do the exact same example of rain or shine, but here's the difference. The difference is that you and I are in different microclimates. If you choose the valley and I choose the valley, because I'm assuming that we're IID, then you have a 75% chance of surviving, and I also have a 75% chance of surviving, and those are two independent draws now in this context. So let me run the simulation in this case with IID environments and show you what we get. In this case, the economists do win. In this case, selfish, optimizing, rational behavior persists. Why? Because the probability that it rains on all of us at the same time when we're in the valley is vanishingly small because it's IID, right? It's not perfectly correlated. It's statistically independent. And so the bottom line here is that nature abhors an undiversified bet. When we're all in the valley and we're all subject to the exact same systematic risk, we get wiped out every once in a while. That behavior won't persist. But in this case, where behavior is itself diversified, where the chances that we will get selected out are vanishingly small, then the selfish optimizing behavior can persist. So ultimately, whether or not a behavior is rational or irrational, the answer depends on the environment that we're in. It's the environment that matters. Do you have systematic or idiosyncratic reproductive success? So there's lots of other extensions of this mathematical framework. There are several papers that we've published, most recently a working paper that's on our website. You're encouraged to take a look at that. But I want to turn now to how this relates to actual behavior from the experimental sense, the neuroscientific perspective. And to do that, I want to tell you about a branch of neuroscience that was developed over the last maybe 20 years on trying to understand what we really mean by rationality. And I'm going to refer to a book that was published about 20 years ago by a neurologist by the name of Antonio Damasio, titled Descartes' Error. Now, Damasio is a clinical neurologist, which means that in addition to doing research, he also sees patients. And in this book, Damasio describes the behavior of a patient that really changed his thinking on what rationality means. And let me tell you about that patient. So patient Elliot was an accountant that ultimately developed a brain tumor that had to be surgically removed. And in doing the removal, they also had to remove a healthy portion of the brain to make sure that they got all of the brain tumor. And after the recovery from the surgery, they gave Elliot a battery of tests to see whether or not his cognitive abilities were impaired. And what they found was that there was absolutely no impact on any of his cognitive functions. Memory, perception, learning, language, arithmetic, all of his abilities were either at average or well above average levels after the surgery. The odd thing was that his behavior had changed to such a point that his wife left him, he was fired from his job, and he ultimately had to be institutionalized. He couldn't live on his own because his behavior was so irrational. And this is how Damasio describes Elliot's behavior. When the job called for interrupting an activity and turning to another, Elliot might persist nonetheless, seemingly losing sight of his main goal. Or he might interrupt the activity he had engaged to turn to something he found more captivating at that particular moment. The flow of work was stopped. One might say that the particular step of the task at which Elliot balked was actually being carried out way too well and at the expense of the overall purpose. One might say that Elliot had become irrational concerning the larger frame of behavior. So let me give you an example of this. Elliot was an accountant, and so when he went back to his job after the surgery, he was asked to write a letter to one of his clients. So he did that. He fired up the word processor, and he was about to start typing, but before he did that, he had to choose just the right font for the letter. And it took him 3 hours to pick the right font. Now, I know all of you have done this before as well. You pull down the menu in Microsoft Word, sans serif, Arial, Calibri. You went down the list. But my guess is that even the first time you did that, it probably didn't take you 3 hours to pick the right font. It took Elliot 3 hours, not only the first time, but every time he had to write a letter after the surgery. Every time, it took him 3 hours. The flow of work was stopped. Each step of the task was being carried out way too well at the expense of the overall purpose. And it wasn't until they gave Elliot one task that he finally failed at that they understood what happened. The task that the psychologists gave Elliot was something called an eye blink response test. And the way it works is that they take a subject and sit him or her in front of a computer screen, and they put electrodes on your eyelids. And these electrodes are meant to measure when you blink your eye. It captures electrical stimulation so that when you activate your eyelid muscles and blink, it captures that. It turns out that for normal human beings, when we are looking at an image that's emotionally evocative, things like a Nazi concentration camp scene, traffic accident, pornography, things that are highly emotionally charged, you blink your eyes a little bit more quickly than normal. I suspect that you're all familiar with that because, for example, in cartoons, when you have a female character that's supposed to be trying to flirt with another character, the way that you express flirtation is how? You bat your eyelashes. You blink a little bit more quickly, right? Or those of you who play, does anybody here play poker? A really serious poker player? Anybody? I know you won't admit it, but I'm sure that there are. Serious poker players know that when you look at somebody's eyes, when they look at their hand, if it's a very strong hand or a very weak hand, you will blink your eyes a little bit more quickly. That's why serious poker players, they wear sunglasses. It's not just to look cool, it's to hide that kind of information. Elliot had absolutely no change in eye blink response rates after the surgery. And that was the answer. He had no emotional response. And it turns out that without emotion, you actually can't be rational. Now, that's what Damasio called Descartes' error. So Descartes is the French philosopher that said that logic is at one end of the extreme, and emotion is at the other end of the extreme. And we ought to stay on the logical side and shun the emotional side. Damasio's results said that's wrong. In fact, logic and emotion are like yin and yang. They actually have to come together. Without emotion, you actually can't be logical. In Eliot's case, because he didn't feel stress or anxiety or concern, he had no problem spending 3 hours writing a letter. And ultimately, he got fired because he got nothing done. He was not capable of meeting a deadline. And so that's where emotion plays a role. It gets us out of bed to work, to finish deadlines, to submit that grant proposal, to do the referee reports, to do all the things that we don't want to do because we want to achieve higher goals. We need emotion to do that. So I'll tell you one more thing about the brain and then show you some actual interesting experimental evidence that finally tells us where Homo economicus resides. It has to do with the fact that the brain is not the homogeneous organ that we think it is. The brain is actually comprised of different components. In some cases, they work together. In other cases, they compete. So neuroscientists identify 3 of them in particular. The brain stem, which is the part of the brain that connects the brain to the spinal cord. From the evolutionary perspective, it's the oldest part of the brain. The brain stem controls very basic bodily functions like breathing, heart rate, skin, body temperature regulation, all the things that we cannot control unless we are Zen Sufi masters. The second part of the brain is the midbrain. That's the part that we share with warm-blooded creatures, mammals. Reptiles don't have this. This is the part of the brain that controls things like fear, greed, love, sex, joy, things that we associate with other mammals, the so-called warm and fuzzy kind of creatures. And from an evolutionary perspective, it's much newer than that brain stem, which is why mammals have it. Reptiles don't have that part. Finally, the part of the brain that we think of as the brain, the gray matter, the curly coils, they're actually not coils. That's the part of the brain that is the newest, hence it's called the neocortex. It's basically a piece of flesh or tissue that's about the size of a dinner napkin, 5 business cards thick. It's stuck on top of the midbrain, and it's sort of scrunched together to fit into our brain casing, which is where you have all of the fissures. It turns out that this part of the brain is responsible for what we associate with the highest functions of human thought, things like mathematical ability, logical deliberation, language, music, things that are unique to Homo sapiens and a few of the great apes. It turns out that these 3 different parts of the brain do different things, and they have different priorities. So let me give you an example. If you are in a car accident, God forbid, and you're bleeding and your body goes into shock, your body starts to shut down. These 3 pieces of your brain will shut down in a very specific order. Which piece of which of these 3 pieces do you think shuts down last? Which has the highest priority? Of course, the brainstem, because you've got to breathe, your heart's got to beat. If that stops, pretty much that's game over. You're done, right? So that has absolutely highest priority, which is why when you are in that situation, you can lose consciousness, but you're still alive, right? The other parts of the brain shut down, but you're still breathing, your heart is still beating. Okay, how about the other 2 pieces of the brain, the neocortex and the midbrain? Which do you think has higher priority from an evolutionary perspective and a physiological perspective? What would you guess? The midbrain? That's right, the midbrain. Why do you say that? That's right, it is. Emotion is actually quite important for survival. For example, if you're being chased by a saber-toothed tiger, it's more important for you to be scared and run like hell than for you to be able to solve differential equations, even if you're from MIT. So in fact, it's true. Scientists have actually documented this, but let me tell you how they've done that. They've taken a subject and put them into an MRI machine, and I suspect many of you have had MRIs. You go into that tube, and they take images of your brain and other parts of your body. Neuroscientists take images of a patient's brain over many, many different snapshots Because it turns out that blood, particularly the flow of blood, shows up on an MRI because blood contains iron, and iron has magnetic properties that actually show up on an image. So you can actually see the blood flowing in the brain if you take many, many snapshots and basically make a movie of the brain. And here's what neuroscientists discovered. They take a patient and they put them into an MRI machine, and while the patient is in the MRI machine, they ask him or her to solve simple math problems, arithmetic, multiplication, division. And the way you do that is there's a little mirror taped at an angle on top of the tube. So you're lying down and looking up. You can see a computer screen projected from the outside of the tube, and your hands are free so you can control a mouse, and you can basically solve math problems on the computer while you're in that magnet. And they're taking an image of the brain, and it turns out that right here, this part of your prefrontal cortex, right around here, that's where the blood goes to flow. And they say that that part is really where you engage in mathematical reasoning. So while you're doing that, they take a needle and they stick it in your leg. And you go, ow, that hurts. And this part of the brain, the midbrain that feels pain, that lights up. And then the flow of blood is reduced to the neocortex. And it takes you longer to solve math problems after you get stuck in the leg. Now, when I first came across that, I said, really? You need an NIH grant to figure that out? I could have told you that if somebody's trying to stab you, it's going to take you longer to solve math problems. But here's the thing. What they documented is that hours after that pinprick, hours later, the flow of blood was restricted to the prefrontal cortex. The effects were very long-lasting. You probably heard the advice that if you suffer a great emotional trauma, one of your family members dies, you go through a divorce, something really terrible happens, you should not make any life-altering decisions for a year. You should wait, right? That's actually good advice, because what's going on is that as your emotional centers are being stimulated, it is actually reducing the flow of blood to your prefrontal cortex so that you are impaired from making good judgments. In fact, people have documented this in many different contexts. I'll show you one in particular, but one that all of you are familiar with is dating. If you've ever been in a situation where you're trying to ask somebody out on a date, you've probably concocted this incredibly sophisticated plan where you will meet this person accidentally, and you will be able to say something that will get the other person to think you're so charming that, yeah, they would love to go out with you on a date. And so you plan this for weeks, in some cases months. And then the appointed time arrives, and you meet this person by accident, and you have your script ready to go, and you start talking, and as soon as you open your mouth, you stutter, and you say all of the wrong things. You embarrass yourself. It's horrible. It's a disaster. Do you know why that is? It turns out that sexual attraction stimulates your midbrain. That reduces the flow of blood to your prefrontal cortex, where language ability resides. For all intents and purposes, love does make us stupid. And so it's real. But I'm going to show you an example of this, not quite that graphic, but an example of how different parts of your brain fight with each other. And it has to do with something called the Stroop test. This is something that a psychologist came up with years ago to illustrate how the different parts of the brain work. What I'm going to ask you to do is to say out loud as quickly as possible from left to right the colors of the different words you see on the page. I don't want you to read anything. I just want you to identify the colors and say them as quickly as possible with me, right? Okay, you ready? All right, here we go. Red, green, blue, yellow, orange, blue, brown, red, green, purple, pink, black, blue, yellow, green. Very good. So now we're going to do the exact same thing, but with this. I want you to say the colors out loud as quickly as possible, right? Ready? Okay, here we go. Blue, red, white, black, yellow, black. Oh man, you're terrible. That is absolutely terrible. What happened? What happened is that in the first case, the word and the color agreed. But in the second case, they didn't. It turns out that color recognition is processed by the midbrain. Language ability resides in the prefrontal cortex. And it turns out that when the two are in conflict, it takes your brain a split second longer to adjudicate that conflict. And so this tells us that our brain is not a single organ. It's actually multiple competing organs. And our behavior is really the outcome of that competition. So the last thing I'm going to tell you about neuroscience, and then we'll move on to implications for finance, is something that was done years ago by neuroscientists called split brain experiments. So you probably know that the brain is comprised of a left hemisphere and a right hemisphere, and they look pretty symmetric. They are symmetric. Well, Roger Sperry and Michael Gazzaniga, two neuroscientists in the 1950s, decided to do a very interesting experiment with certain patients for whom these two hemispheres were surgically separated. Now let me explain what that is. So these two hemispheres, the left and the right sides of the brain, are connected by a thick bundle of fiber called the corpus callosum. It turns out that for certain patients that have a disease called intractable epilepsy, their brain has these electrical storms that spread and cause them to get into these uncontrollable fits. And these epileptic seizures can actually be life-threatening for these patients because they don't know when it's going to occur, they don't know how long it lasts, and if they're driving or in front of a train and they get these seizures, they could die. It turns out that doctors decided, I don't know who the first one was that made this decision, but they decided that because there's these electrical storms that cause seizures, that maybe it would be a good idea to slice the brain in half and cut the corpus callosum so that the electrical seizures couldn't spread from one side of the brain to another. Anyway, it turns out they did it on a patient, and it worked amazingly well. It eliminated the seizures entirely. And so this corpus callosotomy, this procedure for splitting the brain in half, has actually become a surgical procedure that even today is practiced. Now we have drugs to deal with it, but in certain cases of intractable epilepsy, the drugs don't work as well as splitting this corpus callosum. So what Gazzaniga and Sperry did was they studied patients that had this surgical procedure, and they noticed something really interesting. So first of all, you have to understand how the brain is wired. It's a very strange thing. In particular, the way that we see, the way that our visual fields work is that our right visual field is actually connected to the left brain, and the left visual field is connected to the right brain. There's actual circuitry that sort of gets crossed. For evolutionary reasons, this occurred, and it's persisted. And so what Gazzaniga and Sperry did was they showed subjects that had their brains split. They showed them different things in the left and the right side of the field, and they would ask them questions about it, and they observed some really, really strange answers. So let me give you an example. So they would show a split brain patient a screen with a line down the middle, and they would show two different images, one on the left and one on the right. On the left, they might show, or the right, they might show a chicken foot, and the left, they might show a scene of a snow-covered car. And so they would sit the patient in the middle right here, and they would have the patient look at that screen dead on so that the right eye, which goes to the left brain, sees the chicken foot, and the left eye that sees the snow-covered scene goes to the right brain, okay? And they would show them this image, and then they would ask the subject to choose two other images that are most closely associated with the previous one. So let me show you again these images. This is what the patient saw, different things in the right and the left. And then they're showed the same things in the right and the left now. They're showing now one screen. They can look at the whole screen with both eyes. And they're asked to pick two of these things that are most closely associated with the previous image. They're actually asked to use one hand to pick one and another hand to pick another. So, which two do you think are most closely associated with the previous images? Can you tell me? Yeah, exactly. The chicken and the snow shovel. Why the chicken? What does that go with? Yeah, the chicken foot. Why the snow shovel? What does that go with? Yeah, the snow scene. Okay. So this is what the patient did. So they asked the patient to pick, and the patient correctly picked these two. Now, the way that the patient did it was interesting. They asked the patient to use the right hand. The right hand picked the chicken foot. And then they asked the patient to use the left hand, and the left hand picked the snow shovel. But then they asked the patient, why did you do that? And here's the really interesting thing. So the patient said, oh, I picked the chicken because it goes with the chicken foot. Well, why did you pick the shovel? I picked the shovel because you need the shovel to clean the chicken coop. Now, this is very strange. They would ask the patient more and more about the choices, and it became clear that the patient was not able to describe anything about the snow-covered scene. The snow-covered scene was in the left visual field, which is connected to the right brain. Language ability is actually in the left brain, and the left brain is connected to the right visual field. So the left brain is able to describe the chicken, but the left brain didn't see the snow-covered field. And so the left brain has to come up with a reason why the patient picked that shovel. And so it created a reason. And so this is the first time that Gazzaniga and Sperry came up with the notion that the left and the right brains do different things. In fact, what the left brain does is construct explanations, hierarchies, narratives. And it doesn't understand why the right brain picked the shovel because it didn't see the snow. So it created an explanation for what happened. Normally, the left and the right brain communicate with each other through the corpus callosum. But once we severed that, they don't. That's the beauty of this experiment. So it turns out that Sperry, who won the Nobel Prize for this and other experiments, ultimately came up with this interpretation, that the left side of the brain is where executive function resides. It's where planning, hypothesizing, forward-looking behavior, rationality, the way we think of it, engages. Whereas the right side of the brain is really observation, attention, data collection, not analysis. And so finally, we figured out where Homo economicus lives. We live in the left side of the brain. That's what's going on. The problem is that we also have the right side of the brain, and the right side sometimes dominates the left, depending on the circumstances. So I'm going to start wrapping up now, and happy to open it up for dialogue. I'm going to tell you one more thing before getting into the financial implications about how all of this works. And this has to do with the way we model intelligence, both in economics and outside of economics, particularly in artificial intelligence. I want to talk about the fact that, we think about intelligence in a very different way today than we did 10 years ago. And it actually has to do with some online shopping that was at the early outset a breakthrough in how we start implementing new AI. So let me give you an example. A few years ago, I got interested in biomedicine. I started reading various books about biotechnology. So I thought I would order a book about one of the most well-respected biotech companies in the history of the industry called Genentech. So I did what most of us would do when we order a book. I get onto Amazon, and I look for Genentech, and I see it, and I click Add to my shopping basket. And as soon as I do that, Amazon does this thing that I find absolutely really annoying, nasty, obnoxious. What they do is they show me 5 other books that people bought who also bought my book. And sure enough, I had to have at least 2 of those 5. So I end up spending way too much money. This is an example of artificial intelligence. But it's a very different kind of AI than we used to do in the 1970s and 80s. This is an example of using large amounts of data with relatively simple algorithms. The algorithm that Amazon uses basically is, let's figure out all the other people that are just like him, and then figure out what they bought when they bought this book, and show it to him, and let's see what happens, right? The algorithm is almost trivial. What's difficult is getting that large amount of data. That's the real value. That's exactly the opposite of what AI was in the 1970s and 80s. In those days, we had very complicated algorithms, these so-called expert systems, because back then we didn't have a lot of data, and we couldn't store a lot of data because storage was expensive. And so it turns out that this kind of machine intelligence, large amounts of data, relatively simple algorithms, that's part of the new AI, and it's actually much closer to human intelligence. And let me show you an example of that. I'm going to illustrate to you how all of us engage in the kind of machine learning that Amazon does. The example I'm going to give you has to do with something that all of us are hardwired to do, which is detecting threats to our existence. And one of the best ways of detecting threats is using our visual cortex. So I'm going to show you an image in a minute. I'm going to ask you to tell me if this image is threatening or not, friend or foe, okay? So here's the image. Friend or foe? Anybody? Can you tell? You can't tell. There's not enough information, not enough data. This is small data, not big data. And so our visual cortex really has nothing to say. All right, let me show you this. Friend or foe? Friend. Friend or foe? Can you tell? Still can't tell. It's more data. It should sort of look a little familiar to you, but you still can't really tell what's going on. All right? So let me show you a higher resolution image. So this is yours truly. I'm wearing the exact same color outfit. And here, I'm being stalked by a ninja. But you can tell that it's actually not a real threat. This was taken by yours truly as a selfie at the Washington, D.C. Spy Museum. And so this is a statue of a ninja. So clearly, not a threat. We can tell that it's not a threat because of the amount of data that is there. And by looking at the smile on my face and the context, it's pretty clear that there's no threat. We use big data and machine learning in very sophisticated, quick ways. So now let me give you a little bit more of a complex narrative about how we use this and show you what this means. So at a cocktail party that you might attend, you typically will run into different people with different backgrounds and characteristics. And during the course of the evening, you will be spending your time trying to determine whether or not they're friend or foe, whether or not you might like to spend time with them, you might like to work with them, you might like to hang out with them. And so let me give you some examples. During the course of the evening's conversation, you might find out about their gender, about their sexual orientation, and assuming that there are two broad categories of each, there are 4 possibilities there. You might find out about their race and ethnicity, and assuming that there are 4 major categories, you'll find out about that. Their age group, current home state in the United States, there are 50 different states, religious affiliation, and so on and so forth. So I'm going to tell you about 2 different people that you might run into during the course of an evening's conversation, Jose and Susan, and I'm going to ask you questions about them. Now, I realize that this is largely for a US-based audience, so you may not be as familiar with the characteristics of the United States, but I suspect most of you know enough about it to be able to make a judgment on whether or not Jose or Susan are suited for certain contexts. So let me tell you about Jose. Jose happens to be a young professional gay Latino male living in California, Democrat, middle class with an MBA. All right, that's Jose. Susan, on the other hand, is a middle-aged, white, heterosexual female from the state of Texas. She's Christian, Republican, affluent with a Bachelor of Arts. That's Susan. So now I'm going to ask you 3 questions about these 2 individuals, and I want to ask you to make a judgment about them. First question. You're doing a technology startup here in Science Park, and you're looking to hire somebody to work with. Who would you most likely hire, Jose or Susan? How many of you would hire Jose? Show of hands. How many of you would hire Susan? Okay, let the record show 1 person would hire Susan. Most everybody would hire Jose. Okay, second question. You're organizing a fundraiser to raise money for breast cancer, and so you need to have somebody work with you to plan that fundraiser. Who would you hire to raise funds for breast cancer, Jose or Susan? How many people would hire Jose? How many people would hire Jose? How many people would hire Susan? Okay, let the record show everybody would hire Susan. Third question. You are working at the United States Internal Revenue Service as a tax auditor to see who might be cheating on his or her tax returns. who would you audit? You can't audit both of these people because you don't have enough time. You have to audit one or the other. Who would you audit, Susan or Jose, for cheating on tax returns? How many of you would audit Jose for cheating? Wow. How many of you would audit Susan for cheating? Yeah, most of you. Okay. That's really amazing. I cannot believe how judgmental you people are. I mean, you know nothing about these people other than a few facts, and yet you're making judgments on who to hire, who to fire, who's going to be arrested for tax evasion. Of course, I asked you, you didn't volunteer this information, but look how quickly most of you did not hesitate to make a judgment. It's because all of us, all humans, are highly attuned to making quick decisions based upon a relatively small number of features. We're doing what Amazon does. But here in this context, there's actually quite a lot of information. How much information is there? Well, if you go down the list of the different characteristics and the different combinations, it turns out that there are 345,600 different unique individual types. That's more pixels than there are in a 600 by 800 photograph. And so if you think about this as a big data matrix, for those of you who are big data specialists, if you think about this as a big data matrix, what we're trying to do is we've got 345,600 cells that we're trying to fill, and over the course of our lives, we have experiences in meeting various people, and we'll put them into these different cells. And what we're doing when I ask you whether you would hire Jose or Susan for a breast cancer fundraiser or a tech startup, you're looking in your database, like Amazon does, of all the people that you know in these different categories, which one of them has successfully done a startup, which one of them has successfully organized a breast cancer awareness function. The problem is that Amazon has a lot more data than we do. By a show of hands, how many people here have met more than 345,600 people in their lives? Yeah, I actually was in a situation where somebody raised his hand. Turns out to be a marketing guy, not surprisingly. Most of us have a very, very sparse matrix. But from an evolutionary context, it's actually really important for us to make decisions quickly. We can't have the luxury, like a tenured faculty member, of spending years and years on a research project. You have to decide right now. And that's where the problem comes. In many cases, this is not enough data to make a decision, but from an evolutionary context, that's what we're given. And it protects us in many ways, but in this modern era of information, it creates a lot of problems. This is one of the biggest challenges with fake news. Fake news is basically a measure of a means of my changing your measures of the various different databases that you've got stored in your brain. I can change, even if I can change 1 or 2 cells, I can completely change your behavior. And that change in your cell of your various different outcomes, it can actually determine your reality. So let me give you an example of how sparse data can actually change your behavior in very unexpected ways and change reality as a result. To do that, I'm going to give you one final example, which has to do with this scene. Does anybody recognize this? Very good, Harvard Square. How many of you have actually ever visited Harvard Square? Show of hands. Okay, quite a few of you. How many of you have ever driven a car into Harvard Square? How many of you have ever struggled to find parking in Harvard Square? Yeah, it's horrible. It's terrible. In fact, years ago, I decided never, ever to drive my car into Harvard Square. That was my rule of thumb. That was in my brain. My sparse matrix showed that I could never find a parking space in Harvard Square, so it would never, ever be smart to drive into Harvard Square. Until somebody gave me a secret formula for how to get a parking space in Harvard Square. Now, this is really amazing. It's an algorithm that increases the probability of my getting a space in Harvard Square. I'm going to share that with you now, mainly because most of you won't be going to Harvard Square, so you're not going to be competing with me. Let me tell you what the algorithm is. Before you get into Harvard Square, if you're driving, pull over or at a stoplight so you can do this safely. Close your eyes and say the following phrase. Say, Rabbi Mahoney, Rabbi Mahoney, Rabbi Mahoney. Say that slowly 3 times, and then you're done, and you can go to Harvard Square. And if you do that, you will actually increase the probability of getting a space in Harvard Square. Now, I know you're skeptical. You probably don't believe me. I didn't believe it either until I tried it out. And when I tried this, it actually worked. Now, it'll actually work not just for Harvard Square, but for any place that's hard to get parking. So if you're trying to get parking in central Hong Kong, try that and see if it works. And you know what? If you're too embarrassed to try it, tell your friend and let your friend try it. Your friend will come back to you and say, oh my God, thank you so much for this incredible algorithm. Now, I'm absolutely serious. This really does work. The question is why it works. Well, no. It's pull over before you get into Harvard Square, way before you get it. Yeah, so that's not it. But you're on the right track, actually. So let me tell you why it works. So I actually went and did this. I measured the various different times and the likelihood of getting into a space, and I looked at the different spaces that I was able to get. I kept a record of this over 5 or 6 trials. And I finally figured out what was going on. So let me tell you why this algorithm works. So first of all, if you're going to do this algorithm, then implicitly in your database of all outcomes, what you have done is to acknowledge that there is now a slight chance that you will get a space if you follow the algorithm. I mean, if you don't believe it at all, you would never even do this, right? It would be a waste of your time. So the fact that you're willing to try to do this means that a small portion of your brain believes that it can work. So number one, I've already changed one of the cells in your data matrix. Second, I noticed something about my behavior. Now that I believe with a small probability that this could happen, when I drive into Harvard Square, I drive more slowly because I'm expecting that there might be a space. I also look more carefully down the side of the street to see whether or not there are any tail lights that turn on, brake lights by parked cars that are about to pull out. I also drive more carefully while people are crossing the street. Instead of trying to run them over, as I usually do in Boston, I let them cross in front of me because they might be going to a car that would allow me to get a space. So it turns out that my belief changes my behavior. You all heard the phrase, I need to believe, I need to see it to believe it. Well, what I just described to you is the exact opposite. Sometimes you need to believe it before you see it. Your belief changes your behavior, which changes your reality. So you agree with me that if I change my behavior, the probability of getting a space is definitely higher. Because if you don't ever drive to Harvard Square, the probability of getting a space is 0, right? If you assume it's impossible, you won't even try, that's 0. And so by the very act of my belief, I now have changed my reality. So in the last few minutes, I'm going to skip through most of this, but the bottom line for this adaptive markets framework is that it allows us to model behavior in a very, very specific way. It allows us to first of all, acknowledge the role of the environment in shaping our behavior. And secondly, it acknowledges that Homo economicus is an important part of our brain. It's that left brain, but we also have a right brain. And for most of us, the left and the right are connected, and they sometimes compete with each other. And that means that a lot of the things we take for granted in finance doesn't actually work. Let me skip over this and talk about this one, the risk-reward trade-off. We all acknowledge in finance that there's a risk premium for taking on risk, right? And here's the risk-reward trade-off. Large stocks have an average return of 11%, 10%, volatility of 18%. Small stocks, more risk, more return. Treasury bills, much less risk, much less return. The risk-reward trade-off clearly applies over long periods. What if you looked over shorter periods? So what if you looked over 5-year rolling windows of risk and reward? If you did that, let me show you what you get. This is a graph in red of volatility using daily returns for the aggregate US stock market, rolling window 5-year daily return estimates of volatility. And in blue is rolling 5-year estimates of annualized expected return. And what you see from this graph is that risk and reward are negatively correlated. High risk in the 1930s, high volatility, low average return. Lower risk in the 1940s, higher return. Higher risk, lower return, lower risk, higher return. Over 5-year windows, the risk-reward trade-off not only doesn't exist, it's the wrong sign. You actually get punished for taking risk. Why is that? It's because the risk-reward trade-off over long periods of time works. That's the left brain showing that people need to be rewarded, properly compensated. But over short periods of time, we tend to react emotionally. For example, when the stock market does this, when you have this kind of huge drawdown, as you did between the fourth quarter of 2008 and the first quarter of 2009. Sorry, I teach MBA students, so I have to use sound effects to keep them awake. It's like a roller coaster ride that causes us to take money out of the stock market and put it into the bond market. We react with fear and with greed emotionally. So over any shorter term period, like a 5-year window, and 5 is not that short, but over 5-year sub-windows, the risk-reward trade-off actually can be incorrect. So this is an example of this new investment paradigm that's emerging. When you compare efficient markets to adaptive markets, you see that a lot of the things that we take for granted may not actually be true. So let me conclude by pointing out that, it takes a theory to beat a theory, as someone once said. And it's like the old story about the 5 monks who are blind from birth. They encounter an elephant for the very first time in their lives, and the monk that grabs the elephant's trunk feels it and says, an elephant is just like a snake. And the monk that grabs the elephant's leg says, an elephant, it's just like a tree. They're not wrong, but they don't have the complete picture. So we have to think about human behavior as having been stable for a long period of time, but our environment has shifted dramatically over the last even 10 years. And so we adapt to those kinds of changes in very strange ways in certain circumstances. And ultimately, that's what drives financial market dynamics. It's that kind of adaptation that was brought home to me in a very personal way many years ago when my younger son was turning 5 years old, and the older one was at the time 10. And so I remember that day very clearly because the older one was quite jealous of the younger one's birthday. And so he would say to his younger brother, well, Wesley, today you're 5, but I'm 10. I'm twice as old as you. I'm twice as strong as you. I'm twice as smart as you. Basically, I'm just twice as good as you. And it got his younger brother very frustrated until dinner time when the younger sibling came up with a response. I saw his face light up, and he said, Derek, you're twice as old as me, right? Derek said, yes, I am. And Wesley said, that means you're going to die first. So if you understand that, you understand the adaptive markets hypothesis. Thank you. We have time for a few questions.
Yes. Thank you very much, Professor Lowe. Amazing talk. First time I see a talk where someone can weave his life journey so intricately with his research.
Thank you.
It's wonderful. So we actually don't have a lot of time for questions, so I'm just going to open the floor for any questions you may have. Anyone? Yes?
Thank you, Professor, for giving an amazing lecture. I've actually got something which is kind of stuck in my mind, which I hope you can shed some light on. Is that our economics and financial theory has been serving humanity very well for the last 50 years. If you look at rational optimists or enlightenment now, like Steven Pinker, a lot of it, the contribution is actually due to our economic framework. But after the GFC, the financial industry has a bad rap because we're kind of price idolization, very selfish. And your talk about having to move, if we're in a stable environment, economists want, to now we have to be 75% invested in the valley and 25% in the bottom of the valley. How do we engage our discipline for people to actually recognize that there's an altruistic element to what we do to serve the overall community or civilization? I'm kind of struggling with that right now because of the institutionalization that we often see so much with disruption from technology. Thank you.
Yeah, so that's a great question and a very big question. I'm not sure I can do justice to it. I'm going to actually answer that in 2 parts. The first of which I'll just spend a couple of minutes, but the second part of the answer will be a much longer one. That'll be my talk this afternoon. So if I could, I'd ask you to come back at 4:30 when I can give you a much longer answer about how finance and economics in general can play a more positive role in society. But let me give you a quick answer, which is you're absolutely right that finance in particular has definitely seen some very difficult times over the course of the last 10 years. This year is the 10th anniversary of the financial crisis. And we've seen that finance, when it's abused in ways that wasn't intended, can create lots of devastation and harm. I would argue that that's actually human nature. We are all groping for the appropriate ways of deploying our powers. And in many cases, we ultimately end up abusing them because we simply don't know well enough. And it requires a certain kind of adaptation and experience to understand how to wield that kind of power. I think that we can do a better job. And the way that we can do that is by first recognizing that the human element is really key to understanding these kinds of dynamics. And if I had more time, I'd actually talk a bit about how the implications of the adaptive markets hypothesis would suggest different forms of self-governance that would be more or less successful. For example, there's been a very long-term debate between capitalism versus socialism or communism. And particularly here in China, where we have an amazing growth story in a very different system than the US-based system, it's a wonderful thing to discuss. It turns out that the modern version of capitalism and the modern version of socialism, neither of those versions actually really exist in reality. Capitalism, the way that economists think about it, free enterprise, let the market bear whatever it will, and let prices fall where they may. No economy that I know of actually exhibits free enterprise in that way. Even the United States, it doesn't. We have social programs, we have all sorts of regulations, we control prices in many markets. So it's pretty clear that human nature actually affects these kinds of social systems in very, very specific ways, which is one of the reasons why capitalism in its purest form is not sustainable, and socialism in its purest forms is also not sustainable. It's because both of these different forms of governance actually have the incorrect view of human behavior. One of them views humans as being highly rational and efficient. The other one views humans as being social, caring, and loving. Both of them are aspects of our brains, but they actually interact with each other. And we need a blend of the two. So the short answer, believe it or not, this is a short answer, is that there is going to be an optimal blend of capitalism and socialism. And that blend is sort of where the United States and China are actually converging. They come from different ends of the spectrum, but they're actually getting closer and closer, aren't they? That's part of the evolutionary process. And I believe that if we understand human behavior in a deeper way, we can actually get to that sustainable form of what I call neo-capitalism. We can get there much more quickly, but we're not there yet.
So maybe I'll try one. I really appreciate all these explanatory examples you used to support your adaptive market theory. For someone who works in artificial intelligence, I'm curious whether you think it is possible for us to distill the mechanisms in your theory and embed them in, say, a robo-trading algorithm. I mean, I'd be interested in investigating that.
Yeah, so that's a really interesting topic as well, particularly from my perspective, because I've been spending the last few years focusing on robo-advising and trying to come up with algorithms of human behavior. So let me first say that when you're applying artificial intelligence to finance, I think that artificial intelligence is not what we need. What we actually need is what one of my graduate students calls artificial stupidity. We actually need algorithms to model human behavior. And I think it's a bit unfair to call it stupidity. I think it's artificial humanity that we're looking for. We need algorithms, mathematical and statistical algorithms that capture what people really do as opposed to what we think they ought to do. Once we have an algorithmic description of investor behavior, we can then start to design algorithms that counteract that behavior. For example, we often criticize investors for not investing in the stock market in the long run, right? You should just put all your money in the stock market and leave it there and forget about it. That's good advice, but it's not realistic because humans aren't going to do that. If you put your money in the stock market, all your retirement wealth in the stock market, and you're, say, 65 years old, and the stock market goes down by 20%, are you going to sit there and say, oh yeah, I'm going to invest for the long term and not do anything? No, you're going to engage in a behavior that I call freaking out. You're going to freak out, and you're going to say, wow, this is really bad. I'm going to take my money. I got to take some of it out of the stock market. And it turns out that that behavior is actually not that bad a thing to do. The bad thing is when you take money out of the stock market and you forget that you have to put it back in, and you leave it out for too long. That's the bad behavior. And so what we need to do is to start using artificial intelligence to capture realistic modes of human decision making and then develop other algorithms to counteract that kind of behavior to be able to protect investors from their own worst nature.
Perhaps last question?
Yeah, I noticed that this is a technical question. I noticed that there's an assumption underlying the model. So the offspring's behavior exactly like the parents. So what do you think the role of mutation?
Yeah.
I'm working in operations research area. We have a genetic algorithm. So we do need mutation to explore a little bit the global optimality. So what do you think about?
Yeah, that's a great point. If I had more time and my slides actually worked properly so you could see the math, I would have answered that along the way. So you're absolutely right that we did not discuss a very important part of evolution, which is mutation. The model that I described, behavior gets passed down perfectly from one generation to the next. Well, it turns out that mutation is pretty important, as you saw with my first example of the economists getting wiped out. Because once those economists are wiped out, they're gone forever. Mutation is the way that nature allows us to actually bring back certain behaviors that are gone from the population. And why is mutation important? Mutation is important when the environment shifts continuously to other kinds of regimes. Because if it turns out that at some time in the future we need economists, we want that behavior to be there, mutation is the way to bring it back. And so the one thing that we didn't talk about is how mutation gets in here. We have a paper that just describes mutation. It's coming out in another couple of months. It basically models mutation as a very simple algorithm. With 99.9% probability, your children will be just like you. If you're an F, they're an F. But with 0.1% probability, they'll be F prime, where F prime is anything uniformly other than F. That simple description basically allows us to model mutation in a very, very clear way. And that 0.1%, it turns out that that number is directly related to how quickly the environment changes. If the environment changes a lot, then you want mutation to be at a greater rate. And if the environment is relatively stable, then you don't need a lot of mutation. But clearly, that's hardwired in us. And in fact, the way that we get mutation in most cases is through sexual reproduction. So you probably all know this, that sex is good. But the reason that sex is good is because it allows us to actually generate all sorts of really interesting random mutations, except that in certain cases, those mutations can actually cause serious disease. And that we're going to talk about today at 4:30. And finance will actually have something to say about how to deal with that as well. Great. Thank you.
So in the interest of time, we have to end the Q&A session here. Again, please be reminded that we have a public lecture coming up this afternoon. That will be in the Li Xiaopei building, lecture 307. But before we close